An additional important reaction of carboxylic acids is their conversion into amides. Let's draw a general scheme for that reaction, and then we can talk about the details. So this is the general structure for carboxylic acids, and this is general structure for amides. Let's say, for example, NHR, something like that. Now NHR prime should come from the corresponding amine. So NH2 therefore R prime. And of course amines, as you recall, are basic. That's because of the lone pair on nitrogen. And that's of course an important property of amines is their basicity. If simply an amine is mixed with a carboxylic acid, the amine will act as a base. Obviously carboxylic acids are acidic, so what will the amine do is actually deprotonate carboxylic acids in an acid-base reaction. So the mixture of these two compounds or reagents is not efficient or is not good for the conversion of the carboxylic acid into the corresponding amide. So another reagent is actually used, and that is DCC, dicyclohexyl carbodiamide. DCC, we will draw the structure of DCC. So this DCC acts actually as a coupling reagent to activate carboxylic acids and facilitate the attack of the amine in a subsequent step. We will see this mechanistically very, very soon. Let's now think of a possible mechanism for the conversion of carboxylic acids into amides by employing DCC and an amine. So let's draw the structure of carboxylic acids again. This is the structure of carboxylic acids. DCC stands for dicyclohexyl carbodiamide. So this is the structure of DCC. So that's DCC, dicyclohexyl carbodiamide. So what happens first is actually an acid-base reaction between the basic nitrogen and the acidic proton of the carboxylic acid. We can actually redraw this OH bond like this now. So the lone pair on nitrogen is used to make a bond between nitrogen, which is basic, again, that basic nitrogen, and this acidic proton. So an acid-base reaction, something like that. We take an arrow from that lone pair to this hydrogen, and the hydrogen-oxygen bond is then broken, releasing electrons to oxygen of the carboxylic acid. So what do we get? Let's write the intermediates that we have obtained so far. We have the carboxylate ion. We have the carboxylate ion because the carboxylic acid has undergone deprotonation as a result of the reaction of DCC with them in this acid-base reaction. Let's draw the DCC conjugate acid. So this is the other intermediate that should form. So what happens next is that the carboxylate ion, being a nucleophilic, will attack this carbon. This carbon is actually now even more electrophilic, not only because of inductive effect, obviously, by nitrogen or resonance, but also because that nitrogen bonded to carbon has a positive charge. So this carbon is now actually made more electrophilic, so it is susceptible to nucleophilic attack, and that nucleophilic attack will be done by the carboxylate ion. So the carboxylate ion attacks that electrophilic carbon, and the carbon-nitrogen bond is therefore broken, releasing electrons to the positively charged nitrogen. Let's draw the intermediate that are obtained. Okay, so what do we have? We have this unit. Oxygen now bonds to that carbon. There is an H obviously here, and and a cyclohexyl unit. And obviously there is still a carbon-nitrogen double bond. So that's the intermediate that's obtained so far. If you look at this mechanism so far, the amine has not taken role. Okay, so what happens first is actually a reaction between DCC and the carboxylic acid, okay, to activate basically the carboxylic acid to facilitate basically, or in other words, the attack of the amine in a subsequent step. And that subsequent step is actually now. So the amine comes in, if you like, RNH2 prime. And this is, of course, the nitrogen. And that's the lone pair on nitrogen. So the amine attacks that carbon. The amine is a nucleophile. That carbon is electrophilic because of inductive effect and because of resonance. The carbon-oxygen double bond is broken. It's reformed again. And this carbon-oxygen single bond is broken to make a double bond here. And now the carbon-nitrogen double bond is broken, releasing electrons to nitrogen. So let's see what we have. This is one intermediate that's obtained, and the other one is this. Now, so this is actually another intermediate that's obtained along with that main organic intermediate. Now, what happens now is actually deprotonation here, deprotonation there, which can be done very easily. So we can assume that this deprotonates that hydrogen, and the hydrogen-nitrogen bond is broken, releasing electrons to the positively charged nitrogen. Now this, of course, furnishes now the desired amide, whose structure is this. Plus, if you look at the byproduct now, it's dicyclohexyl urea. Actually, this unit is actually urea. So the byproduct is dicyclohexyl urea. Which is obtained as a byproduct in this reaction. So this is a possible mechanism, therefore, for the reaction of carboxylic acids with the DCC in the presence of an amine to give the corresponding amine. DCC acts as a coupling reagent, if you like, or as an activating reagent to activate carboxylic acids, facilitating subsequent attack of amines here at this stage after the carboxylic acid has been activated. Not only the corresponding amide is obtained, dicyclohexyl urea is also obtained, which is basically the material that's left of DCC as a result of all of these mechanistic details.